Hi everyone, thanks for tuning in. My name is Skylar Schultz. I am a formulation chemist here at FCT Solder, and today we are super excited to talk about our newest innovation in our process amplifying series called AMP Micro. So to start, we'll just go over a quick overview of AMP Micro and its general attributes. Then we'll talk about miniaturization of electronics and why there is a need for Type 6 solder paste. And then we'll talk about, as a formulator, what challenges you face when you start working with Type 6 and Type 7 solder powders. Then we'll go on to the experimental design that we have ran in the lab to challenge the solder paste. Essentially, these are pretty difficult tests that we put the paste through. It's not exactly what it'll face out in a customer situation, but it is testing for worst case scenario to figure out where the paste fails. And we'll talk about the results of those experiments, including IPC testing results, reflow data and photos, Tack life results, 8-hour print and pause or stencil life, and then we'll also look at voiding results. Then we'll go into conclusions and a Q&A. AMP Micro is a no clean flux. It is halide and halogen free. It is compatible with industry standard lead-free alloys, including but not limited to SAC 305 and SM100CB. Has excellent printability through ultrafine apertures, and it is air reflow compatible. So if you are a customer who needs to make a transition to Type 6 solder paste and you do not have nitrogen reflow installed, it's not necessary for Type 6 as it is air reflow compatible. And just kind of as a FYI, after doing some research, I found that installing nitrogen in a medium-sized assembly can cost up to like $50K, and installing it in a high volume assembly can cost up to $100, plus any reoccurring nitrogen usage costs. So you definitely save on some nitrogen costs up front, but if you do have nitrogen reflow and you're working with Type 6, Type 7 solder paste, you don't need to use as much. You can have a lower nitrogen ppm. And then, complete coalescence in convection air reflow down to 4 mils, or a 102 micron aperture size. Best in class voiding performance. Long-lasting stencil life of greater or equal to 6 hours, and then a high tack that is stable for 72 hours. This is super important when talking about this high type realm because we are working with such small components that if there is any significant amount of downtime between print and pick and place and reflow, say for your AOI, and your paste loses its tack, it won't hold on to that component. And so this paste retains its holding force over component because it does not lose tack over time. And we'll go more into depth in the results section on tack. Okay, so as an introduction, why do we need a Type 6 solder paste? Well, the industry has been and will continue to trend towards miniaturization. This slide just shows over time how electronics have got more complex, they've gotten more compact, and they require smaller apertures and more advanced packaging. So while in the 1970s and 1980s we had through-hole components with plenty of space around them, then we moved on to surface mount technology, which was like chip scale packages, BGAs, that got more complex, and now we are just densely packaging that into a smaller device. And now we need finer solder powders to print through smaller apertures for applications like package on package, system in package, wafer bumping, and just really semiconductor level packaging and precision is what is needed here. Type 6 and type 7 powders are what you will need to be doing that for like sub 100 micron pads. So this slide here just looks into the industry standard imperial component sizes. And as we can see looking at the image, there has been a substantial reduction in size. So let's say from 0402s, where we're looking at a 40 by 20 mil component, maybe that used to be the norm, but now we are starting to develop solder paste that can print through apertures that are needed for 008 004s, which is a 10 by 5 mil deposit, or aperture size. So very small, and this is where solder paste like Amp Micro come into play. One way that assemblers decide on which powder size to use in their application and for their specific PCB is through the 5-ball rule. The 5-ball rule essentially states that the smallest stencil aperture should be at least 5 times greater than the diameter of the biggest solder particle. So for a type 6, that ranges from 5 to 15 microns. You take the 15 and you times it by 5 to get 75 microns or 3 mils. So with 7, it's 2 mils. However, in practice, we have seen that you will get a more consistent, reliable print if you use more around a 5 to 7 ball rule. So we suggest that with type 6 powder, your smallest aperture should be 4 to 5 mils, and with type 7, it should be 3 to 4. Going into now the challenges of formulating flux for type 6 solder paste, it all really comes down to the surface area. So looking at the chart, we can see that from type 3 to type 6, there is a very substantial increase of 3.5 times the amount of surface area. And so when you have higher surface area of powder, you have higher oxide content. And because of that higher oxide content, your flux formula has to have increased activity. Now, the challenge with that is that there's also a balance, obviously. So if I put too much activity in, that gets rid of that oxide, creating a low defect solder joint. It can react. And so it's all about a balance of finding the right amount of activity to handle the oxide without causing solder paste reactivity. But then on top of that, you also have to take into account the oxidation barrier or flux shell phenomenon around the solder particles. This is basically protects it from further oxidation, and then also you have to keep in mind the rheology. So the paste has to be tuned to print through small apertures. I won't get too in-depth on this slide, but this is our print and reflow parameters. This is just a standard ramp to spike profile. You can also find this on the Amp Micro TDS. This is a test board that we use in the lab. Kind of breaks down what you'll see later in this presentation. We have got a graping pattern, which is to detect at what size on both solder mass defined and non-solder mass defined pads the solder paste struggles to coalesce and forms the grapes. Then we have a 0.3 millimeter BGA. This is a 0.3 millimeter pitch. So it is tight spacing. This is something you would see out on a customer PCB. So we test that as well. Then we have a wet spread section, a solder balling section, which is basically just a pad over print, and when that coalesces into a joint, we want to see no balls left behind. And then the print to fail patterns range from 3 to 16 mils, and that 3 mil aperture is the smallest aperture on this board. So for the 8-hour print and pause test or stencil life, we use the AR patterns at the top. The stencil we used was a 2 mil thick laser cut stencil with solder mask defined pads as the ARs, and it ranges from 4 mil apertures, which is very small, to 8 mil apertures. I picked these apertures because it is the most accurate to where this paste will be used out in the field. You will be printing through apertures this size, and so we can kind of see we've got our aspect ratios. There's no violations there with the 1.55 standard, but the aerial ratios are small. But that is why you need a 2 mil. So we have seen that it prints better through a 2 mil than it does a 3/4 stencil. This slide is just a quick overview of how I ran the 8-hour print and pause stencil life test. Basically, I put a bead of paste on the stencil, I print 2 boards to get it going, I get it through the apertures, and then I print an additional 4. Those 4 I use to collect my reflow data, but I measure SPI data on it, and then I pause for an hour. Then I print another 4 boards, measure with the SPI, print it after another hour. So basically I continue on an 8-hour print and pause, measuring volume data every single time. And then in addition to stencil life, I also ran standard IPC tests required by J Standard 004 and 005. That includes viscosity, copper mirror, slump, solder balling, copper wetting, tack force, and then flux reliability standards, including SIR and ECM. There's that stencil life, and then we'll go through reflow data as well. Okay, so moving on to results, we'll first look at some of the IPC testing results. So starting with the left, you can see that viscosity ranges from 750 to 1000 kcps in Brookfield, and then it's 174 pascal seconds in Malcolm, which is a additional viscosity measurement that some people like to go by. Copper mirror was low, meaning there was no copper breakthrough. The slump was a passing result, and you can see with the pictures here that both cold and hot were passing with very minimal slump. Solder balling result, this is an initial coupon, a 4-hour coupon at room temperature, and a 4-hour coupon at 50% relative humidity. So as you can see, there's no solder balls in the flux pools. We have good uniform coalesced joints, so those are preferred results. Then we have a copper wetting result of a pass. There's no de-wetting. Then moving on to flux reliability results, we can see here passing SIR and ECM results on boards without cleaning. So this is the no clean part. So you do not need to clean this flux. It does not form dendrites. It does not corrode. So it is safe on the board. Then here we have our tack life results over 72 hours in both room temperature and 50% humidity. These are consistent. There's no drop in tack over the 72 hours. Again, this is just an extreme test. Boards would never be left out for 72 hours, but this is to show you that loss of tack and holding force over the component is not a concern with this paste. But you might notice that the tack values themselves are higher than a standard type 4 might give. So FCT's AMP1PT, for example, gives a tack life JIS value of about 100 to 110. It's also consistent for that length of time, but it is a lower tack value. And the reason that type 6, type 7 just have naturally higher tack values has to do with the surface area. So because we have a greater surface area, we have a greater area for the flux to stick to. And so naturally, as you progress from 4 to 5 and 5 to 6, you get tackier paste. And then you can also see our single IPC tack values of 97 for amp micro and 56 gram force for AMP1PT. Here is the print and pause or 8-hour stencil life results for amp micro. As you can see, the initial transfer efficiency for amp micro is really great. It's high, and keep in mind these are the 4 through 8 mil apertures. but it does drop over time. This is somewhat to be expected just because it is a type 6, type 7 paste. There is no underside stencil cleaning during this test, and there is no fresh paste put throughout the whole 8 hours. So the same bead that you start with is the same bead that you finish with, and naturally there will be some drop in volume, but at no point is there no volume. To compare that to a standard type 4 paste, our AMP1 PT on a 4 mil stencil ranging from 6 to 16 mil apertures has a stencil life of greater or equal to 8 hours with transfer efficiencies starting from 18% to 100. So a lower transfer efficiency at the smaller apertures because it's a type 4 paste, but there is less of a drop. So you can expect from the type 4 standard paste to see less of a drop in volume than this AMP Micro. But overall, both really great stencil lives. Here we are looking at the AMP Micro voiding results on both a 2 mil thick stencil and a 4 mil thick stencil. No coating on these, but you can see that there is a difference in voiding in stencil thickness because naturally you are putting down less volume on a 2 mil. But for comparison purposes, I measured our AMP1 PT SAC 305 Type 5 paste and AMP Micro SAC T6, and the voiding levels are very comparable. So here are some reflow images of our test board. So on the left you see our wetting spread test. If this hadn't wet and spread, you would see exposed copper. We can see that it did wet spread on all lines. There are some bricks that did not fully coalesce, but this is a complete wetting result. The solder balling, we can see that there are solder balls left behind. That is somewhat to be expected because this is on an Enix surface and it's a type 6 solder paste. However, ideally this would not have balls. And then for the graping result, these range from 7 to 12 mils on solder mask defined and non-solder mask defined pads, and we are coalescing at all deposits with 0 graping. Few more reflow photos. This is the 0.3 millimeter BGAs and a close-up at those BGAs. There is no bridging. There is minor solder balling around these BGA deposits, so these look good. But most importantly, I want to point out this picture on the right. This is our print to fails, and it ranges from 3 to 15 mil apertures. And we can see, zooming in on the 3 mil aperture, that it is fully coalesced in convection air. So we are printing and coalescing down to that 4 mil aperture size without issue, and a 3 mil potentially. All right, so moving on to conclusions. So AMP Micro is formulated for advanced miniaturization, supporting high density interconnect and ultra high density interconnect applications. These are like sub 100 micron pads. So AMP Micro is formulated for applications including system in package, package on package, flip chip, and in the semiconductor manufacturing realm. AMP Micro enables convection air reflow and eliminates the need for costly nitrogen reflow environments. AMP Micro offers excellent printability through ultrafine apertures needed for the industry's smallest packages, including those 008, 004 imperial component sizes. Then AMP Micro, like our FCT's AMP1 PT paste, offers best-in-class voiding performance. And AMP Micro maintains high tack stability for up to 72 hours, ensuring that there is consistent holding force on small ultrafine components. And that is all. Thank you so much for listening, and I'm happy to answer any questions. Thank you.